Everyone. And yeah, thanks for having me, Paula and Jimmy. It's a pleasure to speak to you all, and hopefully I can provide some interesting, I guess, perspective on open source technology because I know probably like many of you here, I've benefited significantly from from people like or companies like Voxel 51 and the Platform 51. So I guess I'd like to share my perspective on how that will transform agriculture. All right, so let's kick it off. So you should be able to see my screen now with the title slide here, and I do think that open source technology will transform agriculture. I think we're missing out if we don't make more of an effort from sort of companies and individuals and everyone to try and put more data out in the open. And I guess I'll explain a bit more about it along the way. But I'm based at the University of Copenhagen, and feel free to get in touch. And there are some links I'll just send as well, so you can see them as I chat. So these are some of the people things I'll reference along the way if you want to follow along. I thought I'd take it back a step, and Chris has expertly covered this as well a little bit. But what is agriculture, and not maybe from the sense of producing food or clothes or animals? It's to me a combination of the environment. So this is a very encompassing term, and things like, of course, the weather, the soil, the plants themselves, I guess, in some sense. It's a combination of environment, genetics, and genetics includes so plants and animals as well. So as we breed new crops or different varieties of food, and then of course different animal genetics too to improve resistance to certain stresses. But it's also a combination of culture, and I guess it's part of agriculture itself is the word culture, because there are so many things that we do and we want that are really defined by where we grow up and the system in which we operate. And so, of course, where I am in Denmark and Copenhagen, people eat different food to, say, the US or Australia, where I've lived before. So culture is such a huge way of influencing agriculture in a whole sense. But of course, this combination is very much a great generator of edge cases. So edge cases really are general cases in my opinion in agriculture. And I know Chris talked about this a little bit before. There's one of the constants in agriculture is change. And part of that story is what I like to think of as field observation intensity. And so if we go back to the maybe 100 years or so, even 50 years, to where people had much smaller farms, there were a lot more people in agriculture, and there was a lot more precise management. I guess I should say my context of all this is growing up in Australia on very large Australian farms, and this, of course, does differ, I guess, depending on where you are. But in Australia, particularly, these farms have gone from relatively small. They've been mechanized, and over time, there's fewer people. And so that level of precision management, where, say, a farmer I talked to, his parents wouldn't clear a certain part of the land because the soil there they knew was bad because the vegetation that was growing there wasn't, well, they knew the vegetation only grew on poor soil. So they didn't clear it. But then it was cleared in subsequent generations, and now he's trying to sort of get back to those smaller fields in a sense. Because what we saw with these larger farms, as farms consolidated and as fewer people moved off the land, then it became these very much large scale management. So in Australia, we saw paddocks or fields, I should say, grow to thousands of hectares in size, a single field. And so we lost that almost precision management just based on the human nature of agriculture of these potentially bad patches. But where I see technology taking us in the future is we can have large farms with few people, but also have lots of sensors so that field observation intensity becomes much smaller again. And so these small squares then end up managing very small, even centimeter or millimeter level analysis of every field. And to me, that is where we can bring back some precise management. And so if you put this in a graphical format, well, we started off with sort of high labor intensity with mechanization that has decreased. So the observations per area to a point where it was very inefficient. And I think Chris mentioned that perhaps we're sort of turning away from that now through digitization, where we can really increase the level of analysis we have on every square meter, square foot, square centimeter, square inch of ground. And that's because, well, edge cases are general cases in agriculture. And if we don't have that a really precise approach, then we're going to miss things. So this is on the left in Australia. Then we have Denmark over here. And what works in Australia was not going to probably work in Denmark, nor in Argentina, nor in Texas, in these places where I've collected image data previously, because all these areas have very different environmental conditions and very different growing environments as well. So it's critical, I guess, that we can manage these edge cases very well. And of course, Denmark and some areas are also very cold in time. So how does this scale, and how does one create a company that scales as well through all of this variability? And how do we build on through this? Because it is very challenging to build something, say, in Texas, and then try and expand that into Australia if you keep everything closed. And I think going back a few years, even probably only 5 years, people thought that deep learning would answer all our problems. At least that's what I was probably considering myself. And although with, I guess, a grain of salt, and people saw that performance would grow with scale, where if you gave it more and more image data, then the algorithm would get better and better. And that was different to, say, traditional machine learning, things like support vector machines or random forests, where you had a much smaller amount of training data that resulted in almost like a plateau of performance that didn't generalize well into new fields. And we've sort of seen this as well with large language models and recent advancements in that field, where they've just been throwing data and throwing compute at the problem to try and ever increase this curve of performance. It was also a very good lecture by Andrew, if you haven't seen it before. And so how do we detect weeds then? Well, I know Chris and Paula have gone through a lot of this. But basically, we have some sort of sensor, and there's a few different categories, I would say, of different difficulties of weed detection too. And there's green on brown, which is where you detect green weeds in a brown paddock, a brown field. And that's basically in Australia during the summer season, where you're trying to manage weeds so they don't consume all the moisture before you plant the crops in the autumn. So Australia's a little bit different. But they do this in America as well, I think, or at least in Canada. I've heard about using green on brown technology. I know the John Deere system, See and Spray, I think it's probably Ultimate or one of those, I think not the top level, the mid-level one, that does green on brown too. So then you have camera-based AI, and this can also be done with sensors that just detect growing plants. But I guess the selectivity is based on the context. So anything that's green in this scenario will be a weed, because you want to try and get rid of it to save water for your next crop. Then we have camera-based AI. So this is where you have image sensors that collect images, and you now analyze them in ways that Paula and Chris have talked about. And for example, broadleaf in a cereal crop is quite a straightforward one. You have very different leaf, I guess, between the wheat and the broadleaf weed, things like wild radish. Then we also have things like grass in cereal, where you might detect more complicated or very similar looking grasses compared to the cereal crop. And that's much more complex. And this is the second half. The green on green is where we're trying to detect weeds in crop. And that's where we want to use more complex weed recognition algorithms. And that's where this idea of algorithms learning comes from. So you have the input image data, and we've seen this a bit with Paula. You tell it where the annotation of the palm amaranth here in cotton is, and then it learns from the underlying pixel data, and then it does this thousands of times to train itself. Sorry, that's going back. There we go. So thousands of images are really needed for developing these effective algorithms. I think the scale of it, when the billions of images that John Deere has or are collecting, you can really see the importance of very large training data sets. So that's the detection, and that's just one aspect of the system. And so there's a sensor basically that records some data, and that in this, I guess, case, what we're talking about, Vision AI, that is generally always an imaging sensor, but it might be multispectral, like we've heard. Perhaps it's RGB, which is much more, I guess, generally cost effective and easier to work with. Even reflectance data from those sensor-based systems too. But that sensor provides that data to a processor. You have a weed detection algorithm, and that weed detection algorithm, if there's a weed, then it tells the controller to spray some sort of chemical. And this is fairly well established. As we've heard, we've got John Deere in the bottom right. We have companies like Bilberry, a French company working with Agrifac, and a whole range of other companies that's in Australia. Eco-Robotics, a Swiss company doing this on a very small scale. In fact, I think I counted there's about 25, 26, 27 companies doing this currently. And I think about 30 if you start including the non-imaging companies as well. So there's a lot of action in this space currently. So there's companies across the world that are working on real-time weed recognition at various scales and various crops, and of course trying to address all those niche cases. The one video I'd like to include, because it's not all about spraying, is this targeted tillage. And these are what's called ratoon cotton or volunteer cotton that comes up after you've had a cotton crop. And this is windmill grass. And this is a detection algorithm that's finding, or it's just a sensor actually, it's a weed system that just finds the green weed with the growing chlorophyll, activates a tine using hydraulic solenoids, and then chips that weed out, just like you would if you're walking through a field yourself and kicked a weed out with your boot. But just to say, it doesn't have to be spraying. It can be a whole range of things. But that's an end-to-end system, I guess. And this move to deep learning and the performance advantages we've seen has really, I guess, been made clear in the research. As this is some of what we did a few years ago with a review of what's been published. But you can see over time on the x-axis here we have 1990. I think some of the first work in image-based weed detection was from the late 80s. And you see accuracy on the left-hand side, and this is machine learning accuracy. So over time, when we had those manual feature extraction, where we had different more basic algorithms, where we decided if we wanted color or if we wanted texture or leaf shape, that's where we extracted them ourselves. And that's in these yellow circles. And often very small data sets, very niche data sets, or from specific fields or specific parts of the world. And normally instead of under 100 images, maybe up to 500, or in some cases, rare cases, 1,000. But what we saw in 2017 was this shift towards uses of deep learning, so things like convolutional neural networks specifically. And that resulted in these sort of much more advanced feature extraction, so we could understand image features much better. And that resulted in a much greater improvement in accuracy that you can see here since 2017, and really allowed us to generalize even further. As that addressed, I guess, that problem I mentioned of how do we scale? And this was one of the beginnings of that ability to. But it's not perfect, and as we're seeing, there's always challenges with this. Because, well, it's challenging to scale because you need large quantities of images, and you need to be able to generalize across all farms and all fields. And every year throughout the season, people want to spray at nighttime. They want to spray in the mornings, at dusk and dawn, after it rains or in the dust. Everything changes the way plants look. Fields, farms, regions, it's all very variable. Of course, the seasonality of agriculture. So while cars, if you wanted to create a car detection algorithm, you can go out today and you go out tomorrow and the day after, and you'll see all these different cars that you can develop your training data set. But if you want this time of year in Denmark, in 2025, with these conditions, having been off a slightly warmer winter with rain just a couple of days ago, well, today is the only chance that you'll get, because in the future it's going to be different temperatures, it'll be different planting dates, it'll be different soil temperatures, everything changes. And perhaps it's imperceptible, that it's not important enough, but there are some changes that are really critical, so you get that coverage in your data set. Then, of course, there's similar looking species that I mentioned, so things like ryegrass and wheat. And then the idea of mimicry: can weeds actually evolve to avoid being detected altogether by looking like the crop? And some research we're doing at the moment suggests that that might actually occur, but very much at the start of that process. And then what is high performance? Because what do people want in the field? What do farmers think is high performance is very different to what you might see in a publication or when you train an algorithm on your computer. And it tells you it's getting 95% recall. Is that good when you put it in the field, or is that bad? And then there's always the challenging different growth stages or the appearance of weeds at the same time in the same crop. These two weeds here are Palm amaranth. They look wildly different. And again, some research we did showed that if you trained it on, say, this one and not the bottom one, then you lose out on the ability to detect the sort of different classes or different weed sizes. So it's really important to cover that in your data set. And there's also this barrier to access innovation, because these systems, like John Deere's, which are exceptional, they're very impressive in what they can do. But they're also very expensive. Either have subscription costs, ongoing subscription costs, high upfront costs, or very sort of inaccessible approaches to fitting them to equipment. The application niche environments, perhaps they'll just focus on large market segments that make the most money for their company, which makes sense. But it means that people in the niche environments that want to use this technology don't have access to it. Then there's, of course, access to public training data for development. And 51 is a really great example of an open source tool that it helps people develop their algorithms. Retrofitting to existing sprayers and also the right to repair, of course. So farmers that can take a technology and just like they used to, perhaps with welders and all that, repair that technology or add a new algorithm. I like to think of it like tractors, they have 3-point linkages. So on the back of the tractor is a way to pick up implements with three different points. You can raise and lower it, and it's fairly standard. So why don't we have that in agriculture? Why can't a farmer go out there and train their own algorithm and put it into a sprayer? And perhaps there's a lot of complications of that, of course. It's not as easy as just training the algorithm and throwing it in your John Deere sprayer. But it's really important that perhaps we consider these new ways of sort of engaging with farmers and technology and trying to remove that black box wherever possible. And it comes down to, well, can agriculture advance faster with open source tech? And I think for all of these above challenges that I've mentioned, I absolutely think it can. And I think we really are missing out if we don't adopt as a whole industry a more encompassing approach. Because if we say use the machine learning industry, for example, where did this phrase about deep learning start? I know this is very high level. I know there's a lot of work that went on before this. But if you look at 2012, there was that seminal paper by Krzyzewski that produced AlexNet, and that's the one everyone cites and talks about. And before that is when the ILS VRC, which was I forget the acronym, but the competition surrounding ImageNet. And yeah, basically who can perform the best on a very large scale image data set. And that gave rise to the Krzyzewski paper, because they could perform on this very large amount of data. But before that, well, then there was Fei-Fei Li, who was starting the ImageNet collection. And of course, before that, you had LeNet back in 1989, I think, with the postcode detection and some of the very first convolutional neural networks. And then before that, of course, then you had all the work on multi-layer perceptrons back in the 1940s. So it's this culmination of all this open source work that led to where we are today. And you can even see that with OpenAI and LLMs, with the Transformer paper that was published in 2017 as well. Attention is all we need gave rise to some of the architectures we're seeing that are doing exceptionally well now. So open source has really enabled it all. And I don't think the term open source is very much technology based. But if you look at the original open source agricultural equipment, well, it's usually been a welder, perhaps a drill, and an angle grinder. Particularly in my case, it's a pretty awful welder. But it's really critical because in the past, when everything was generally steel or easy to operate on, for example, older tractors or chisel plows like we saw, you can adapt them. You can pick them up, change them into new ways that fit your niche use case as a farmer. And so that's why I think open source technology, so sharing this tech recipe is so important, because it allows collaboration globally. I think while welding and angle grinders are good for local stuff, collaboration globally is really important to advance even faster. And this technology really allows us to do that. For example, 51, of course, and I mean, Meta's released a whole lot of stuff, Mozilla under here, and WeedAI, which is one of the links I sent before as an open source platform for weed imagery. And then, of course, recently, if you look at the RoboFlow detection transformer model they just released, but all of these curves here are all open source models too. And we heard that Blue River even started with YOLO V8 and quickly realized, I guess, that it was too heavy, but then still let them sort of get that start. And I think that'd be even more impressive for a smaller company sort of to get headway much quicker. Then there's, of course, error checking. So you make errors, people might be able to find them. Niche use cases, of course, people can build into areas that fit them if we share that base recipe. And that lowers that barrier to innovation, because anyone can start building with it. Anyone can, like Paula mentioned, it was much easier these days to start developing in machine learning than it has been. And if it's easier, then there are more people that can start building it into their specific idea, their specific problem. And so that's why I think it's so critical. And then you get user-driven development. I certainly wouldn't have been able to build anything that I have if it wasn't for open source tools. And I'm trained in agricultural science and in weed science, and I've taught myself about technology over the last few years. And me, I guess, as someone who's a user of agricultural stuff, can then start developing things that I think are useful in this industry. And while I probably don't do a good development job as maybe a genuine developer who was trained in that, I think with the tools these days, it means we can have at least tools that go 90% of the way much faster. And of course, it enables open development and use to encourage that collaboration. And this is a really interesting one. I was looking through the One Smart Spray, which is a spot spraying device as a combination of a joint venture between Bosch, Zavio, and so I just got the third person. But yeah, there's 3 people, I think, that are involved in that one. But they actually list all of the open source tools they've used on this web page here. So you can go and click through and see what they're using for their, I think, field camera unit. There we go. And you can see which of these tools they used. I think they were using things like TensorFlow Lite and I guess what you'd expect. And I'm sure this would also be the case for things like Blue River, where they'd be using a range of some of these open source software. So that's what got me thinking about how I could kind of contribute in this space. And this is one tool I've developed called the OpenWeedLocator. And this is a device that uses, at least at the start when we developed this in 2021, very simple. It was a Raspberry Pi 3 at the time, and it's now become a Raspberry Pi 5. It was meant as an educational and practical tool, so people to learn about coding, because I wanted to learn about how we could develop or code, but with agricultural examples, and I couldn't see anything out there previously. And so you can connect a relay controller to it, a Raspberry Pi camera. Originally, it was just a high-quality camera, and now it's a global shutter. And you just activate one of those relays based on where the weed is, as you can see here. And it was all right. It did a pretty good job of being a very low cost. I think a couple $100 US to build, and people could fit them. And then we moved into the OWL 2.0 the last year or so. And we moved into Raspberry Pi 5 global shutter camera, the Pi Camera 2 library. Now we're getting 60 frames per second at about 640 by 480 pixels, and also added some things like the controllers, as you can see, and also a dedicated hat that you can, you can either buy. My brother designed it for me as a gift, but you can also, all the code and all the files for this are available online on the GitHub that you can get through here or the link that I shared. So it's very much entirely open source, so you can build this yourself. We've done some research on how it performs at different speeds with different plants. So forage oats as a weed, in inverted commas, for like a grass weed, and tillage radish as a broadleaf weed, and also build controllers for it now too. So you can start to control this from the cab of your vehicle for data recording, for spot spraying, for turning all solenoids on. But what you can see here is that this connects to the Raspberry Pi GPIO pins. And then you have these 4 outputs and the 12 volts in, or anywhere between 7 and 26 volts that then is converted down to the 5 volts for the Raspberry Pi. And then you just plug that into the 12 volts of the tractor, turn it on, and the camera will start running. So it's all meant to be completely disconnected from the internet, very basic, very simple to run. And of course, all this stuff is very replaceable and quite cheap. So it's kind of, the idea is to bring that right to repair, the ability to repair to farmers. But what's probably the coolest thing about the OpenWeedLocator is the community around it. So I'm not exactly sure exactly how many countries it's in now, but it's roughly 10 the last time I counted. So places like Australia, of course, where we developed it, Canada, the US, Denmark, France, Germany, New Zealand, as I'll show you next, India, China. People are building it everywhere because everyone wants to have a go at either learning about how to build something with what they have on hand, or maybe building a useful tool deliberately. Now, we've had it on things like little robots that a farmer built in Australia. This is University of Sydney robot. This is back of a ute or a utility vehicle in Tamworth, a town north of Sydney. This is a field day. This is another version we built. This is one in Denmark I built. This is another utility vehicle in Sydney. And this is a guy in Canada. This is one I built on a bicycle. Again, you can fit it to any sort of equipment you want because you've got the code, you have the files to adapt into your niche use case. This is a farmer in Australia who built one, a 4-meter one. Again, I think he just built it entirely himself. I never knew until he sent me this video. I was quite impressed. But you can see the 4 OpenWeedLocator units situated on this boom, and then see him sitting in the cab of that utility vehicle there. This was a guy in New Zealand, and I sent him one of these enclosures and one of the control boards that you saw, and he's using this for his driveway spraying. And I think he started offering a service on another platform that he's built. But again, he built all this electronics himself. He connected it up, and he wanted the ability to visualize when those nozzles are turning on. You can see on the bottom left corner. But again, it's all open, and that means you can do this because everything there is provided. So the future for this OpenWeedLocator is to make it a much bigger system, so it's easier to set up. We're setting up a 12-meter one at the moment. We want a control interface and app so you can start to download data, single line installs, make it sort of accessible as possible. So it's almost like these commercial systems. So everyone can start using precision agriculture, not just the necessarily largest farmers that can afford the most expensive setups. This is one of the platforms we're working on at the moment and currently building. And so this is training on some thistle data in the fields here in Denmark, because we want to be able to do that green on green detection in a sense. This is green on brown, but we don't want to spray every weed here. We just want to spray the thistles because they're most problematic. And that brings me over to open source image data and WeedAI, because images are still the biggest, and I don't think we can ever entirely get around that problem because you won't be able to always collect or always get around synthetic images from a particular region if you've never seen that before. And so I think these are the biggest constraint to innovation. Closed data really does delay progress, but I think commercialization is still possible if there's more open data sets. I guess I'm not saying you have to release every single data set that's out there, but I think there's much greater opportunities to build and to grow as an industry and move into more precise tools if we can share some of those images, at least to get things going. And you can test it out. So I'll just change my screen share. So this is the WeedAI platform. So you can download from a whole range of, I think, about 35,000 different annotated images. These aren't ones I've necessarily collected. I've collected a few of them, but they're ones like deep weeds, which is a very common data set that's used in academia. This one is the Lincoln beet data set, but you can, for example, search by sugar beet, Beta vulgaris, and that will bring up a few different data sets here. So this is the Lincoln beet data set. We click on that, it will then take us to the page, and we can see there are 31,036 images of an unspecified weeds, so they don't have a class, or they don't have a species. Then there's the Beta vulgaris, the crop, and that's got 16,000 downing boxes, 22,000. And to download, you just download it. It downloads it in a COCO format with all this metadata appended at the end. And you go back to the data sets and see this entire list of the ones available. So yeah, more than welcome. You definitely check this out. And it's of course upload. So you guys can also share your data. So if you sign in, accepts all these different formats, so we can keep growing this as a community and increase the amount of image data available to everyone. So I'll just go back to the presentation and just wrap up. We are also collecting as much image data as we can on a range of platforms. So this is a robot in Western Australia. This is some work done at the University of Copenhagen to try and build up as much data as we can get. Because I think we really do need to move away from that sort of black box and more toward the right to repair, but in the sense of like a right to repair algorithms or 3-point linkage of algorithm development. So final observations, I guess, is modern precision ag is really transforming that ability to find weeds and act precisely. And it's really critical that we are really open with research and what we do, and also the data, the algorithms we develop, because I think we can advance much faster as an industry to try and develop these problems, solve these problems, and develop some solutions. And the second best time to plant a tree is today. So we haven't started. Maybe 10 years ago, we'd have huge data sets. We haven't yet started, but it's always good to start now than never. But I gave it to an algorithm, and ChatGPT came up with the and best time is today to plant a tree. So we're getting there. Like I saw that OpenAI released a new image generation model. So thank you, and feel free to check out some of these links, and hopefully time for questions, or if not, get in touch.
All right, fantastic. So I did repost your links from the very beginning of the presentation to WeedAI, OpenWeedLocator, as well as IWRC. Let's grab one quick question before you have to split, Guy. Actually, it's a two-parter. How do you handle seasonal changes? Is it as simple as collecting data from different seasons? I think you covered this in one of your early slides.
Yeah, I mean, it's definitely a challenge, and I think Chris probably knows a bit more about it than I do. But I think collecting in different seasons is one way of doing it. I have heard of some people collecting in the same time from different parts of the world to make the most of, I guess, northern and southern hemispheres. But that is, of course, fraught with some environmental problems. So collecting both seasons is best, or just whenever you're trying to operate your algorithm, collect in that situation.
And the second part to the question, how many types of weeds do you label? Do you retrain models on newer labels if new weeds are discovered?
Yeah, so you label as many, if you're just trying to find a specific weed, say like thistle, that's quite different to everything else around it, then we've just been labeling the thistles and just not caring too much if there are other dandelions or other weeds that get detected as thistles. So of course, you're better off labeling everything in an image to sort of give the algorithm the best understanding of the scene. But yeah, I think what we generally do is just label as best we can. And if there is a new weed that you're trying to detect, then labeling that too. There are some really cool algorithms out there around anomaly detection. Yeah,